Okay, today we start with a topic that is, we continue basically with the topic that was halogens. We did the initial part of the trends and what were the trends for the halogens, how the ionization energy is changing and the colors are changing. Then we talked about its reaction. Now we move on to reaction of the halogens. Now we move on to the next thing that is disproportionation reaction. Disproportionation reaction was done before also. That was in the chapter for redox reaction, but we will quickly review this again. We will review this again. So disproportionation reactions. Now, as discussed before, disproportionation reactions are nothing but they are actually the redox reaction. They are redox reactions, but they are a special type of redox reaction. Special. What is special about them? That it is the same substance. It is the same substance that is oxidized as well as reduced. That is oxidized as well as reduced. While in redox reaction, when we talked about there was one substance that was oxidized and there was another substance, second substance that was reduced. So there were two substances involved. One was being oxidized, the other was being reduced. But over here, it is the same substance that is oxidized as well as reduced. So they do ask in your exam the definition for this. So what is a disproportionation reaction? It is a redox reaction where the same substance is oxidized as well as reduced. Now here we need to talk about, like for example, the reactions which we are required according to your specification is reaction of chlorine, chlorine with water to show a disproportionation reaction. So over here, like for example, you have a Cl2 gas, you add it into water, it forms HCl and HClO. Now, if you observe why we are calling it as a redox reaction and then why you are calling it as a disproportionation reaction, for that you need to write down their oxidation numbers. So chlorine is 0, hydrogen is all its compound is +1, oxygen in all its compound is -2, H is +1, Cl is -1, the H is +1, oxygen is -2, so the Cl will be +1. Now, if you observe over here, chlorine is changing from 0 to -1, that is decrease in oxidation number. Decrease in oxidation number means reduction. And chlorine is also changing from 0 to +1 in HClO. So that means it is oxidation. So what is happening over here is the chlorine is being oxidized to HClO and it is being reduced to HCl. So this is an example of a disproportionation reaction. This is an example of a disproportionation reaction because the same substance is being oxidized as well as reduced. Now we call this as hydrogen chlorate 1. Why do you call it 1? Because of the oxidation number of Cl over here. To show that it is the valency of Cl over here is +1, because usually it is -1, but in this compound it is +1. So you have to specify this. This is one of the reactions which represents the disproportionation reaction of chlorine. The other one is so this was the first example, reaction of chlorine with water. The second one is with cold dilute NaOH or KOH. You can take NaOH or KOH, anything, that doesn't matter. In the exam they can So one of the possible examples of chlorine reaction is with cold dilute NaOH. So they can use the word cold, they can use the word dilute, but cold and dilute always goes together. So in the exam, it will never be hot and dilute. It will always be cold and dilute. So if you have a chlorine, you react it with NaOH, aqueous. This is a gas. Now when you pass it over here, it forms NaCl, NaClO, and H2O. And then you can balance it. And if you want, you can balance it. In this case, what happens over here is, how do we know it is a redox or a disproportionation or not? Chlorine is 0, Na is +1, oxygen is -2, hydrogen is +1, Na is +1, Cl is -1, oxidation numbers, Na is +1, Cl is +1, then the total is -2. So the total of all this will be 0. This is +1 and this is -2. Now, if you observe over here, it is 0 to -1, which means it is reduction, and it is 0 to +1, which means it is oxidation. So again, this is an example of a disproportionation reaction. The name for this salt would be sodium chlorate 1, to show that this is chlorine is over here is +1 oxidation state. Now remember, this is under cold and dilute condition. If this was with hot and concentrated, so it will never be hot and dilute. It will be hot and concentrated NaOH. Same reaction, chlorine plus NaOH. Now in this case, this is hot and concentrated. You get NaCl plus NaClO3 plus H2O. So over here, this is okay. Let's find out the oxidation numbers. This is 0, this is +1, this is -2, this is +1, this is +1, Cl is -1, Na is +1, oxygen is -2. Each oxygen is -2, so total is -6, and this is +1, that means +5. So the chlorine over here is +5, and then this is normal, +1 and -2. Now if you observe over here, the Cl2 is changing to -1. This is reduction as before, while the Cl2 is changing into +5. So this is oxidation. So this also is an example of redox reaction. This is known as sodium chlorate 5. Why 5? Because the oxidation state is 5 over here. This is a reason. So these are some of the examples which are related to chlorine undergoing a disproportionation reaction. But in the exam, they can give you anything as such, and you know how to find out the redox reaction. And if you figure out that the same substance is being oxidized or reduced, that would mean that it is a disproportionation reaction. So these were just few of the examples. Some of the examples were taken before when we did the redox reaction. So we did this thing. This is the use of chlorine in water treatment. Why water treatment? Because this HCl and HClO form, it works as a germicide. It kills the germs in the swimming pool or in the water. And they said to form a bleach. So actually chlorine and NaOH combination is used as a bleach. This combination is used as a bleach, chlorine and NaOH. This helps in the combination of NaClO and NaClO3. It helps in disinfecting or cleaning or bleaching action. Then we move on to the next part, that is this thing. Now this is something very, very important. This is even required for your unit 3. So let's talk about this now. So here we need to focus on right now this part. where they said solid group 1 halides with concentrated sulfuric acid. So this is the first time you are studying reaction of concentrated acids, and this is something very, very important. So over here, what we will do is we will try to do the reactions of group 1 halides with concentrated H2SO4. So we are doing the reaction with concentrated H2SO4. Now, when you say group 1 halide, it means I can take NaCl, KCl, anything, and halide, what we will do is we will take one time NaCl, another example we will take NaBr, and the third time we will take the example of NaI. So these were the three different halides. Now Na is a spectator ion. I'm teaching you maybe in terms of Na. In your exam, they may give you in terms of K, Cl, Kbr, and Ki. So that doesn't matter. So let's start with the first one. So the first one is with NaCl. So remember, you are doing the reaction of NaCl with concentrated H2SO4. And another important thing is, if you look over here, they said solid. You are using solid. So you are not dissolving it in water or anything. So the reaction will be NaCl. Okay, before that, an important thing is we did last lesson was, before this, the important thing which we did last lesson was that when you talk about reducing strength, when you talk about reducing its agent strength of reducing agent, we have understood that the reducing strength increases this way. So keep this in mind. Keep this thing in mind, because we will need this concept. It's actually, this reaction is a concept for this application of this, the reducing strength of the halides. Remember, these are all halides, not halogens. These are all halides because they are the ions. So okay, so let's talk about first with NaCl. Now when you're doing it with NaCl, what happens is you can take NaCl plus H2SO4. Now it forms NaHSO4 plus HCl. Now instead of this, you can write Na2SO4. It's the same thing. The only thing is then you will need a balancing. If instead of NaHSO4, you are writing Na2SO4. Otherwise, everything remains the same. So you can write either of this. Both will be considered as correct. Now, the first and the most important thing is they will ask you, there are questions in your past paper where they ask you the state symbols. Now for the Na, the state symbol will be solid because you are taking solid. Now this is concentrated H2SO4. This will not be aqueous. This will be liquid. So that is something important. This is solid, and then this is a gas. Why HCl is a gas over here? Because there is no water over here. So HCl will be produced as a gas. The next thing is they can ask you related thing is, what is your observation over here? Now observation over here is, this is your white residue, not very important. All group 1 and group 2 and all, except transition metals, the rest of the salts are white. So this is a white residue. That is not an issue at all. The important thing is this. So this is your first observation you can talk about. The second observation is steamy fumes. Now steamy fumes represents this HCl. So we will study later on how to confirm this. So I would say we will do the test for this. Test to confirm whether this is HCl. Now steamy fume is a observation for HCl. If you were doing this reaction with NaBr, or there is somewhere HBr gas form, it will also be the steamy fumes for HBr, and same way for the HI. So steamy fume is an indication of the hydrogen halide gas being produced. So in your exam, they need this word steamy fumes, which indicates steamy means too much of steams will be coming out. We will learn how to understand or how to test whether it is actually the HCl or some other thing. Another thing is we need to figure out whether this is a redox reaction or not. So if you observe over here, Na is +1, Cl is -1, H is +1. Now sulfate overall, because this sulfate and this sulfate is the same thing. So I will take overall for this -2. This is +1. This is +1. This is -2. This is +1. This is -1. Now if you observe over here, there is no change in oxidation number. Now if there is no change in oxidation number, it means this reaction is not a redox reaction. So this is something important. This is not a redox reaction. So with NaCl, you get an observation as a steamy fumes. This is the important observation. We will be talking about it further. And this is not a redox reaction. That is an important thing over here. Now, if you move on to the next one, that is with NaBr. Now, I'm using NaBr. It could be any group 1. So in your exam, they may give you KBr. That's the same thing. If you react NaBr, remember it is solid. You react it with H2SO4. Remember it is a concentrated, so you will write it a liquid. It will form NaHSO4 plus HBr. But the problem here is this HBr is a good reducing agent. It is a good reducing agent. HCl was not a reducing agent, good reducing agent, because if you observe over here, when you have the Cl minus ion, it is not a good reducing agent because as you go down, the reducing agent increases. So the Br is a better reducing agent. So what it does is, the HBr being a better reducing agent, it reduces. So therefore what happens is the HBr reduces the H2SO4 to SO2. Now, if it is reducing something, then the H itself, it is oxidized to Br2. Therefore, instead of writing this reaction, because this HBr will react with the H2O further, because it is a good reducing agent, what you can do is you can write down the reaction as NaBr solid plus H2SO4 liquid. It gives you NaHSO4 solid plus, don't write the HBr, instead of that write the final product plus the bromine gas or liquid. You can write gas or liquid because at room temperature it exists as a liquid also, but because the heat may be generated due to the presence of or the reaction with concentrated H2SO4, so there is a chance of bromine being a gas. Better write a liquid, gas. But by mistake, if you write liquid, they may accept it. But better write a gas because heat is being generated as a concentrated H2SO4 is being used. So it will change from liquid to gas. So at the end, this is your final reaction. So you had a final reaction with a NaCl, this one. Here the reaction stops because HCl is a weak reducing, Cl minus is a weak reducing agent, but here it goes one step further. So this is your final equation. Now let's try to figure out whether this is a redox or not, and what are the observations and so on. So let's start with, first of all, whether this is a redox or not. Na is +1, Br is -1, this is +1, sulfur is +6. We have done this before. Oxygen is -2, so you know how to calculate. Over here, Na is +1, H is +1, sulfur is +6, oxygen is -2. Over here, sulfur is +4, Br is 0. Now, if you observe over here, the Br is changing from -1 to 0. So this is an increase, oxidation. This is what we said over here. The Br minus HBr changes into, so basically the Br minus ion is changing into Br2. So it is being oxidized, and the sulfur over here is from +6 is changing into +4. So this is being reduced. So this gives us an idea that this reaction is a redox reaction. That's the first thing. The second thing is they can ask us is about the observations. What are the observations? Now, you may have a pungent smelling gas. There are many gases which are pungent smelling. So we can assume that the pungent smell is because of this. We can assume it, but we will do the test for it. So all the test at one place. The other observation would be for the bromine, which is a reddish brown gas. Reddish brown gas. So this will be an indication of bromine, but again, we will have to confirm it. So the importance of this is that the Br is a good reducing agent. So as a result, further reductions or reactions take place. And as a result, you end up with sulfur dioxide and Br2 instead of HBr, which makes it a redox reaction. And these are your observations. So we will talk about the test later on. The next thing is with sodium iodide. With sodium iodide, now what happens is the NaI, again, you are reacting it with H2SO4. Remember, NaI is solid, this is concentrated. When it reacts, it forms NaHSO4 plus Hi. But the problem is, this is a very good reducing agent, or we can say the strongest reducing agent among the halides. So what happens is now the Hi reduces the H2SO4 to SO2 like HBr, but it is a strong reducing agent, very good or a strong reducing agent. So it does not stop over here. It further reduces it to H2S, and the Hi gets oxidized to I2. So again, here in H at when you are reacting with the HBr, the reaction stopped or the reduction stopped over here because HBr was good enough only to reduce the H2SO4 to sulfur dioxide. But Hi is a strong reducing agent, so it is able to go one step further and reduce the SO2 form to H2S. So this shows it is a stronger reducing agent compared to the Br minus. So your final equation would be will be NaI solid plus H2SO4 liquid, that gives you NaHSO4 plus H2S from here plus I2. So I2 you can say gas or solid, better say gas, and H2S is a gas, and you will have some amount of water also over here. You will have some amount of water also formed here. Actually, water will also be formed over here also. If you will go for the balancing, you will find water is also formed over here. Now, so that's the first thing. So your final equation is this. This is your final equation, and that is because the I minus is a powerful reducing or a strong reducing agent, so it is reducing it further. Now, if you want to know whether this reaction is a redox or not, what you have to do is just look at the oxidation numbers. Now over here, I will only write the oxidation numbers for the things that are changing. So I minus is -1. Sulfur over here is +6. Sulfur over here is +6, so there is no change. But over here, the sulfur is -2. Sulfur is -2, and this is 0. So what is happening is the I minus is changing into 0, increase, that is oxidation. We already said iodine is formed due to oxidation, and the S in the sulfur in H2SO4, it changes into S-2, it decreases, which means it is reduction. So this is also a redox reaction. This is also a redox reaction. Next thing is the observations. Next thing is the observations. Now, what are the observations? Definitely white residue. That is not very important. The important thing is, again, there is a gas given, a rotten smell, rotten egg smelling gas given out. Now, this is actually an indication of H2S. So for H2S, you use the word rotten egg. We will test for it whether it is actually raw H2S or not. And for iodine, since you are writing it as a gas, observation as a gas, so you can say purple or violet vapors. So that would be an indication of the I2, but we will have to confirm it through the test. So what we have learned about this is that I2 is I minus is a powerful reducing agent, so it reduces the SO2 further to H2S, and this is also a redox reaction. Then the next thing is we need to confirm all the things that we have been talking about, that this is H2S produced, this is SO2 produced, or I2 produced, and so on. So let's start with the first thing is the test for HCl. Now this is actually for all of them, HBr or HI, anything. This will be helpful for your unit 3 also. Unit 3 also. So over here, and all these observations and everything, they are required for your unit 3 also. So over here, there are two ways of testing this, whether it is HCl or not. Bring a glass rod dipped in ammonia solution. Your observation would near the mouth of the test tube, near the mouth of the test tube. Your observation will be, now again, a very important thing, your observation will be dense white fumes. So you have to write dense white fumes. This dense white fume is ammonium chloride, or if it was bromide, then instead of chloride you would have a bromide, or instead of bromide you could have an iodide, depending on what you have. But all of them they give the all of them will provide the dense white fume. So this is something important. What is happening over here? Your HCl gas, which is coming out from the test tube, this vapors, which you are calling it as steamy fumes, you bring a glass rod, bring a glass rod over here. Now what happens is, suddenly you observe dense white fumes, too much of fumes. So what is happening is the HCl reacts with the ammonia, which is sticking on the glass rod, and it forms ammonium chloride. So instead of fumes, you can also call it as a solid. So you can also say this is white solid formed on the rod. Why? Because this has a property of sublimation. So the ammonium chloride has a property of sublimation. So you can even write in the observation white solid on the glass rod. So if this is one of the tests to confirm, the other test is bring a wet, or you call it as a damp, or you call it as a moist red litmus paper. We did this when we were talking about the test for ammonium ions. So bring a rod wet, damp, or moist red litmus paper near the mouth of the test tube. You will the red litmus turns to blue. So that is indication of ammonia being basic. So right now, ammonia is the only basic gas which you come across. So that confirms HCl. So these two reactions or these two tests will confirm. No, I'm doing it wrong. You don't bring a rod, dip in with a red litmus paper. That is for ammonia. You bring a rod dip in ammonia. Just like there's no need for this. This is a test for ammonia. You are testing HCl. So this is enough. Bring a glass rod or a paper dip in. That's enough. I was thinking we are testing ammonia. You are testing for HCl. You're testing for HCl. So this is enough. Next thing is, so we did the test for the HCl. The other gas that was coming out was sulfur dioxide. So we will test for sulfur dioxide. Now for sulfur dioxide, what happens is this is a gas. So pass the gas. Either you say pass the gas, or better is bring a paper. That's a better way, because there are many things that are coming out from the test tube. So what you do is bring a paper dipped in potassium dichromate solution near the mouth of the test tube. Near the mouth of the test tube. So what happens is orange paper turns green. If it turns to green, it means sulfur dioxide is present. If the gas coming out is sulfur dioxide. Now, why this is happening? This is happening because the dichromate ion Cr2O7 minus in acidic medium, this is an oxidizing agent. This is an oxidizing agent. Just like KMnO4. Just like KMnO4, it is an oxidizing agent, and this is orange in color. So when you dip the paper in filter paper, usually we dip it in a potassium dichromate solution. It absorbs the dichromate solution, potassium dichromate or sodium dichromate solution, and the paper will have like orange color. Now, this being an oxidizing agent, what happens that it oxidizes the SO2. It oxidizes the SO2 to SO3. It oxidizes the SO2 to SO3. So therefore, once it is oxidizing this, the dichromate ion itself will be reduced to Cr plus 3. So the dichromate ion is orange in color, but when it gets reduced to, why it is being reduced? Because it is an oxidizing agent. When it gets reduced to Cr plus 3, the Cr plus 3 is green in color. So this can only happen, dichromate can change only into Cr plus 3 when the SO2 is being oxidized to SO3. So the change in color to green is an indication that the SO2 gas is being oxidized to SO3. So this is how you confirm SO3. If the color is changing, it means it is SO2 gas which is coming out, which is being oxidized, and the dichromate ion is being reduced from orange to green. The next thing is the test for iodine. Now this biology students, they know it. Test for iodine, simple thing, turns starch solution into blue black. So you get a blue black appearance when you take either a starch paper or a starch solution and you put it near the iodine gas which is coming out. So that's a simple thing, test for I2. Then the last thing is The last thing is the test for H2S. The test for H2S. Now, test for H2S is you bring a paper dipped in lead ethanoate solution near the mouth of the test tube. Your observation would be the blue black or black solid or paper turns black, whatever you want to write. Paper turns black. It's actually the lead ethanoate solution which was sticking on the paper that turns black. So a black solid or PPT, whatever you want to write. Depending on if you are passing H2S gas into a solution of lead ethanoate, then it will be a precipitate. If you have a paper, you bring it near the mouth of the test tube, then it will have black deposits over here. So why that is happening? Because the lead ethanoate is CH3COO2 Pb. When you react it with H2S, what happens is this Pb reacts with the S, forming PbS, and you get your carboxylic acid, which is ethanoic acid. This is your black solid. This is your black solid. In one of the exams, they have asked this reaction. They have asked this, what is this black solid? So this black solid is PbS, which is lead sulfide, while the H2S is hydrogen sulfide. So that completes our reaction with concentrated H2SO4. Now moving on to the next part, that is, so over here, I have explained you, if you go back to the reactions which we were talking about, I have explained you the test for iodine. I have explained you the test for H2S. I have explained you the test for sulfur dioxide. Okay, this is left. Bromine is left. Then, so we have talked about the sulfur dioxide. Bromine I will explain now. Then I have talked about this thing. Now bromine, everyone knows. We have been using this test for bromine. Test for bromine. Pass into ethene gas or solution, whatever you want to say. What will happen is the reddish brown color, the reddish brown color of bromine is decolorized. Why that is happening? Why that is happening? We know it. This is actually used as a test for alkenes or unsaturation. When you add this to bromine, it will be this. So this is your reddish brown. This is your reddish brown, and when it converts into this form, which is 1,2-dibromoethane, the color disappears. So this is your colorless solution. So that indicates the test for bromine. Now the next thing is the test for the halides. So remember, before you were testing for halogens. This is Br2. This is your Br2, which is a halogen. Then chlorine. All those things are halogens. Now we are talking about testing for halides. Test for halides. Now, test for halide means you are testing for chloride, bromide, or iodide. That's the most common examples which we take, and it is also mentioned in your specification. Fluoride we don't take, very reactive. And astatine we don't take because it is radioactive, not used commonly in the labs. So what you will do is you will take the salt solution or the salt and you add dilute nitric acid followed by silver nitrate solution. Now, dilute nitric acid means it is aqueous. You just need to add few drops. Now, in the exam, they can ask you why you are adding this. Why? So the answer is simple. You have to say to remove carbonate impurities. To remove the carbonate impurities. And the reason why we want to remove the carbonate impurities is because if you don't remove them, then the carbonates will also be precipitated out as a white precipitate. So that will interfere with our result. So you are adding in a test tube these three things. You are adding in a test tube these three things. The sequence is important. You have to first add nitric acid, remove the carbonate, then you add silver nitrate. If you do the opposite, then that means if you add silver nitrate before and nitric acid later on, then you are not removing the carbonates. Then already the carbonates will be precipitated out. Now, depending on which halide is present, you could have three different observations. It could be a white precipitate, it could be a cream precipitate, depending on or you also call it as a pale yellow precipitate. And depending on the halide which is present in this unknown salt, whether it is a chloride, bromide, or iodide, you will get one of this color, one of the precipitates. Now, if it is a white precipitate, they may ask you which substance is responsible for this white precipitate. So the formula of the substance responsible is AgCl. For this, it is AgBr, and this is AgI. So these are the substances responsible. Now the problem is the colors are very close to each other, means the cream, white, and yellow is very difficult in the lab to differentiate between these colors. So what we do is we do a further test of solubility of precipitates with solubility of precipitate in ammonia solution. So what you will do is to confirm whether the white is actually white or not, or it is something else. So what we do is to the precipitate, that means after you have got the precipitate, add ammonia solution. Now they may say ammonia solution or they say ammonium hydroxide. It is the same thing. The reason is ammonia dissolved in water forms this thing. So whether they say ammonia solution, ammonia water, or ammonium hydroxide, all means the same thing. The white precipitate, if you were thinking of that it is a white precipitate, then what will happen is this will dissolve in ammonia solution, or you can say in the dilute. That means even if you add a little amount of ammonia solution, this will dissolve. Once you know that this is dissolving, you are 100% sure that the chloride is present. So if you are not very sure whether it is white or cream, while looking at the color in the test tube, you just add ammonia into that test tube. Even if you add a small amount of ammonia, the precipitate starts dissolving. That is an indication, that is a clear indication that this is actually a white precipitate and it contains a chloride. While if it was not a white precipitate, if it was a cream precipitate, then it dissolves, but it dissolves in either we use the word excess of ammonia, or excess means more. So most of the time instead of excess, the examiner may use the concentrated ammonia solution. So here it will also dissolve, the precipitate will dissolve, but the condition is it has to be concentrated. This was not here. This was dissolving in even the dilute, less amount. Here, For the cream precipitate, it will dissolve in excess amount. And if it is a yellow precipitate, you are not sure whether it is a yellow or a cream precipitate, then this will remain insoluble even in concentrated ammonia solution. So you add as much as you like, but the precipitate does not dissolve. It is a clear indication that it is a yellow. So if it dissolves in concentrated, you are sure that Br minus is present. If it remains insoluble, you are sure it is I minus present. As simple as that. Now the next thing is we need to, the last thing which, for this topic is which we need to focus on is so right now we have talked about this concentrated HCl, then we have talked about the precipitation of chloride, bromide, iodide reactions and the solubility of the precipitates in ammonia. Now the next thing, the hydrogen halide with ammonia gas. This already explained to you that you take HCl, react it with ammonia, you get ammonium chloride. That I told you with a test for HCl or hydrogen halides, you get ammonium bromide, already explained to you, plus NH3, and this will be NH4I. All these are observed as dense white fumes, and all of these are observed as steamy fumes. So that is done. And then hydrogen halide with water. So hydrogen halide with water. So that means you just add them to water. So if you have a HCl gas, hydrogen halide means the gas part, you react or add it to water, it becomes HCl aqueous. That means it becomes a salt. Now, acid. So this will be known as a hydrochloric acid. Same way, if you have HBr, you add it to water, it will form HBr aqueous. This will be known as hydrobromic acid. And if you have a HI gas dissolved or added to water, it will form HI aqueous. So that becomes an acid, which is hydroiodic acid. So this completes your this part also. So from your specification, we have talked. Now the last thing over here is the last thing over here, which is this thing, able to predict based of for astatine and fluorine. So whatever we have talked about for chlorine, bromine and iodine, everything is applicable over here, except that fluorine is more reactive. Fluorine is most reactive, so all the reactions that are taking place with fluorine will be faster because of its reactivity. It is a gas, its color is light, while astatine is the lowest in the group, so it will be the least reactive. The color is dark, it is solid, but in terms of the formula, the reactions, it will be the same. So they're just talking about the knowledge of the trend in halogen chemistry to make predictions. So basically, how will you predict? That will be based on the position in the reactivity or the group. That's the only thing. And that completes your chapter. This completes your chapter. So over here, your group 7 ends. So next lesson, inshallah, we will continue with the kinetics.